Last video on the banked curve introduction was with the guiding equation. Okay, so now you've got it. Now we're going to apply it in an example. I'm just going to do one example because it's just not that hard. So then you can practice it on your problem set and you'll see. So now that you got this formula, if you're wondering how do I mark, by the way, if I think communication-wise, I like to see the free body diagram on a banked curve question. If you can't remember, you could put it on your formula sheet, and then starting with this equation and working your way down, that would be perfect communication. From an application point of view, you know, I usually mark it in the application section on the test. Probably just being able to apply the formulas is good for me. Okay, but if you can, I like to see that free body diagram. Okay, so here's the example. Here's the information we have. We have a car of mass 1,100 kilograms. And we have a frictionless banked curve. Again, always assume frictionless if it's banked. That example we did earlier, it was not a level curve, and then we counted friction, right? Excuse me. But for anything I'd ever ask you, if it's banked curve, it'll be frictionless, except for your bonus, which is to take this example I just did for you, or I'm going to do for you in a moment, sorry, and you're going to do it again with find the maximum safe speed with a coefficient of friction of 0.6. So in our example here, it's looking for part C, what constant speed must the car maintain? So that's frictionless. Go through, I'm going to do the example in a moment, and I want you to think about that free body diagram. You would so earn your bonus marks if you could take that free body diagram, add friction to it, and come up with a solution to this. How that speed would change. You might just know it would change it. Probably with more friction, you could go faster. That would be a fair guess. Calculate it for me. But you have to come up with some formulas too by using the free body diagram, and that would be impressive. Okay, so first of all, what force provides the centripetal acceleration? Well, we answered that earlier. It's a component of normal, right? Using, I didn't write it, but I should have. That this is our positive y, and this is our positive x. Then, oops, I can use the positive there too, I guess. So we said this earlier, we said this in the last video, that the vertical component is equal to gravity, and the horizontal component is equal to circular centripetal force. So what is the force that provides? It's a component of normal, right? Fnx. Then it says draw a free body diagram of the car and determine the normal force. So far we're just looking for normal. And how you would do that is use the y direction balance and say that, and I'm looking for normal, right? But I can say that mg down here equals Fn cos, Fn cos 19, right? Because remember, this is touching the angle, and I'm solving for Fn. So then just rearrange and solve for Fn. By the way, I didn't check mark it because I'm not going to check mark it because I don't know normal forces are hard there. I guess I can check mark it with the idea that I didn't get 0.5 newtons, and because I know that wouldn't make sense. But okay. Part C, now we're looking for what speed? You're looking for v. This is the meat of the question. What you use is the guiding formula that I gave you, which comes out of that free body diagram. And then I'm isolating Fc because, saying that Fg equals mg, that's why this here. So instead of Fg, I'm writing mg. And knowing that Fc has mv squared over r, now I have this formula. M's cancel. Get rid of my M's there. They show up in each term. They're gone. And you end up with rearranging for V is the square root of Rg tan theta, which you could write this on your formula sheet too, because it applies for banked curves. It applies for banked curves, and it is sort of, if you're not too sure about the development here, again, communication-wise, I'm looking for that. But if you can just apply that formula, I'm fairly content with that, okay? And I get an answer of 17 meters per second, which again, multiply by 3.6 just in your head, multiply by 17 by 4, to round it. So that's 3468 kilometers per hour is probably, for a frictionless surface, is about right if you think about a banked stretch of highway or something. In part D, just jumping up, how does the speed required for a more massive vehicle such as a truck compare with that by a car? On the level curve, it made a difference. However, if you look here, I canceled the m's out. This v has nothing to do. I could have m of 50,000 kilograms and it wouldn't affect what the v is. Therefore, mass has no effect on the safe speed on a banked curve with the absence of friction. Okay, so that's really applying the banked curve formulas and everything. Just jumping ahead, I want you to at least write down the bonus, think about it, and sometime when you have some time, just change the free body diagram, add friction, what direction would it be? And then you're looking for, or you have a mu k, or mu s, sorry. And how would that change your free body diagram and the formulas? And give it a go. It'd be good for you. Okay, that's it. That's it for bank curves.